With Chapter 7, we really start talking about inference, where we take information from a sample and use it to kind of predict what would happen with our population. That's the key foundation and the key thing behind statistics, is that you use a small piece of information to say, how does this apply to a larger group? Or you use one experiment to say, okay, well, how does this apply to this situation at large? That's inference. And one of the foundational pieces of inference is a sampling distribution, which is what Chapter 7 is all about. But before we start with Chapter 7, we really need to talk about some definitions, particularly like the vocabulary parameter and statistic. Parameter is a number that describes a characteristic of a population, and it's usually unknown. It's usually represented by a Greek letter. For example, mu usually means the mean. Standard deviation is usually represented by sigma. It's not always represented by a Greek letter, though, because for proportion we just use the letter P. But remember that this is usually unknown. Actually, this is usually what we're trying to find out. A statistic, on the other hand, is a number that describes a characteristic of a sample. These are usually represented by Roman letters, which are our normal alphabet letters. Usually lowercase, and they usually have a symbol. So like, instead of mu, if I'm talking about a sample, I talk about X bar. Instead of sigma, if I'm talking about a sample, I say S sub X. And instead of P for proportion, if I'm talking about a sample proportion, I say P hat. So you're going to hear me say these things: X bar, S of X, P hat. That's how we talk about these. They are related to each other because we use statistics to estimate parameters. Because the parameters are often going to be what we don't know. And it's really hard for me to go through and say, sample all high school students in the United States. Because that would be really time consuming, it would require a lot of resources, it would require a lot of money. So instead, I take a random sample, and then I use my random sample to estimate what the actual value would be. Okay, from here on out, we can't just say mean, because you don't know, or I won't know, if you're talking about the population mean or if you're talking about a sample mean. So this is an AP tip to make sure that you specify from here on out whether or not you're talking about a population or a sample. And you can specify either with the symbol, or you can specify by saying population mean, sample mean, but you cannot just say mean. So let's look at this example. It wants us to identify the population, the parameter, the sample, and the statistic in each setting. So a pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates the third quartile of 56 inches. So our population would be all 10-year-old boys, because that is who she's interested in knowing information about. That's how you determine your population. Who are you interested in knowing information about? Our sample would be the 50 boys in the sample. Our parameter is what she is interested in knowing about 10-year-old boys. And that would be the 75th percentile for the population, which is also Q3. And the statistic is the actual Q3 that she got from the sample, which in this case would be 56 inches. Okay, so if we look at this next one, a Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. Okay, so our population here would be all 12 to 17-year-olds in the United States. Be as specific as they are in the problem. Okay, our sample would be the 1,102 12 to 17-year-olds that were surveyed. Our parameter is what she's interested in knowing. And in this case, because her sample, it tells us that the respondents 71% said yes, it looks like the parameter she's interested in knowing is the proportion who own a cell phone. We don't usually talk about percent, so really this is probably 0.71 is a better way to represent that. We deal with proportions, so it's the proportion who have a cell phone. Okay, since we've gone through this example, let's take a moment and do the check your understanding questions. So pause the video, see if you can answer these questions on your own, and then see if your answers match mine. Our parameter in this case, in question 1, is mu, which is equal to 20 ounces. And the statistic is x bar, which is equal to 19.6 ounces. And in the second problem, our parameter is talking about a proportion here, so we're going to use P, which is equal to 0.1, and our statistic, we're talking about P hat, which is equal to 0.08. So hopefully you got those. Make sure you ask me if you have any questions about the difference between parameters and statistics. One very important aspect of statistics and sampling, especially when thinking about inference, is sampling variability. We have alluded to sampling variability throughout the year without actually calling it that, and actually we may have called it that in class a couple of times. But what it means is that when I take a sample, I'm not going to get the same thing every time. And so if I'm not getting the same actual pieces of data every time, then my statistics are not going to be the same either. So the value of a statistic varies with repeated random sampling. Notice I specify random here because if it's not random, then it's biased and it's not any good anyway. Okay, and you've noticed this because, I mean, that's why we do all of these experiments and all of these simulations in class, and we talk about the results and we send in the results through the Inspires. It's because everyone gets something different. That's what makes statistics so great, and the reason for statistics is that everyone gets something different. And so then you have to weed out through all the different answers what is the best guess or the best estimate for what the real true value is if I use the entire population. All of those different values that occur naturally are because of sampling variability. And it's a huge thing in statistics as long as the variability is just due to the randomness and not the fact that you have biased it in some way. So the sampling variability leads to sampling distributions. And so as an example here, this is my computer program Fathom. It's what I use to curve your test grades. It's what I use to do a lot of different experiments and simulations. And here I have 200 pieces of data representing just chips. 100 of them are red and 100 of them are blue. And what I'm going to do here is tell it to take a sample of these chips. I'm going to take a sample of size 20. Okay, so I'm going to tell it that every time I take a sample, I'm going to replace it. I'm going to do it without replacement. So that's a true sample, like I'm actually picking the chips out of the bag. And I'm going to do 20. Okay, and I can actually see my sample here. Okay, so there's my 20 chips. And if I want to know how many of them are red and how many of them are blue, I'm going to create something. Here we call it a measure in this program, but really it's our statistic. And I'm going to call it the proportion of red chips. And I'm going to tell my calculator here that I want the proportion where the color is equal to red. Okay, so you see here, this value here tells me that approximately 55% of my chips are red in this case, so 0.55. So here, what I'm going to do here now is I'm going to tell this to collect some measures. And so what you're seeing here is that I'm taking a new sample, and every time I take a new sample, it calculates the proportion of red chips for that sample. Then it's taking another new sample and calculating the proportion of red chips for that sample. And so it just did that 5 times. And if I create a table for this, you can see that each of the times I did it, these are my five different proportions of red chips. So here I've taken 5 different samples and calculated the proportion each time. So let's keep going, and let's actually take 500. Every time I take one, I don't want to replace these. So let's take so 500, so 495, and I'm going to turn the animation off. But you will see it flash. And each time it's flashing, it's creating a new sample, and each time it draws a new sample, it's creating and calculating the new proportion. And so it's going to do this 495 times, which will give us 500 total proportions. And we're going to go through this process in class too, with a penny activity that we are doing. So you'll see this again in class. But I wanted to put it on the video just so you would have it for future reference. So it's calculating, it's calculating. So here are our 500 measures, our 500 statistics. So each of these is a proportion gained from a sample of 20 chips. So if I want to see these, really want to see what this looks like, I'm going to take this and let's make a dot plot. Okay, so you can see in our dot plot, our proportions go from, there was one time when it looks like we got about 18% red, and then all the way up to one time when we got about 80% red. And if I have this information, okay, I've taken many samples, I can use this information to help me figure out really and truly probably where the proportion, okay, probably where the proportion of true red chips in the whole population is. And it's probably one of these that I got more of. Because the chances are, if I've done 500 samples, if I only got 0.8 twice out of 500 times, that's probably not the true proportion of red chips. That's probably one of those things that's going to happen a few times because there's always the possibility or the probability that it will. But the things that happen the most often are probably the things that are closest to being true. So I feel pretty confident that my true proportion of red chips is probably somewhere in the 0.4 to 0.5 range. 0.4 to 0.4.5, 0.5. And in fact, we know that that's true because we know the true proportion because we started with a population that had half of its chips being red. But in real life, you're not going to know this population information. It would be as if this was hidden from you and all you had is one of these samples. So what we do is we're going to learn things from information like this, and then go backwards and hypothesize what our true proportion would be. Okay, so if I did this many more times and included all possibilities and of all the samples, if I took every possible sample of 20 that I could take and calculated for each one of those samples all of their proportions and graphed all of those proportions like this, those sample proportions, then that would be called a sampling distribution. And that is what this chapter is all about, and it is what the basis of everything we're going to do from here on out is this sampling distribution and understanding what it is. Okay, a sampling distribution is all of the possible values that I could get if I took all the possible samples out of my population, calculated a statistic from each one of those, and then made a distribution of those statistics. So listed them all out, put them on a graph. Okay, that's a distribution. So this right here is the beginnings of a sampling distribution, but not the entire thing. But you would see that if I kept taking the sampling distributions, if I took more samples here, it would only increase my pattern. My pattern would only get stronger, and these values in the middle would only be more obvious that they are the most common occurrences. So let's talk about our sampling distribution and get the actual definition. The actual definition is the distribution of values taken by the statistic in all possible samples of the same size from the population. I have another AP tip for you. When you are discussing distributions, do not be vague. It is very important that you specify the differences in your distribution. Say it's the distribution of values or the distribution of the statistics or the distribution of the population data. Be very specific in the types of distributions that you're talking about. It's much like parameters and statistics. You need to be very specific about what you are talking about. So this diagram right here is actually a very good representation of what we actually just did. Here are our chips, our population distribution. These are all of the chips that are in the bag. As you can see, 100 of them blue, 100 of them red. So my parameter is P equals 0.5. So from then, I took a lot of different samples. I took 500. And each of those samples are going to produce a different amount of chips, the red and blue chips, and a different statistic, which is p hat. And you can see all of these are different. All the ones on ours were different because of sampling variability. This is what sampling variability describes. Different values for each sample. And then my sampling distribution, okay, if I have taken all possible samples I could take, it is a sampling distribution. It's just a distribution of all of those p hat values. Out of all the times I did this, what values did that p hat take? So this is a very good example. The distribution of the population is all of the possible values and their frequencies in the population. The distribution of the sample are all the possible samples. Okay? And the sampling distribution of the sample statistic is all of the possible values for p hat in this case and the values that it can take. So when you think about creating a sampling distribution, think of this process. You start with the population, you take all possible samples, you take all of the p hats from those possible samples, and you put them in a distribution of them by themselves. So let's look at this. This is what we just did. We looked at that dot plot. In fact, we have it right here. Okay, and our questions here ask us if this is a sampling distribution. And no, it's not, because this is not all of the possible samples. These are only 500 of them. I could take 500 more. So let's look at the distribution. Okay, it looks roughly symmetric. There don't seem to be any outliers. My mean is about 0.5. Okay, somewhere between 0.4 and 0.5. My spread, my range is from 0.15 to 0.8, so 0.65. Okay. So let's say this. Let's say that I have this bag of 200 chips and I'm claiming that half of them are red. A classmate of yours reaches in and takes a simple random sample of 20 chips and 17 of them are red. Based on that one sample, what would you say about my claim that half of them are red? Okay, 17 out of 20. That's a really high value. It's going to be somewhere in this range up here. Okay, as a proportion. So the chances are that, and this is where inference comes in and what we will be doing. We're going to say that the likelihood, and remember that 0.05, we always talk about that 5%, the likelihood of me pulling 20 chips out and getting 17 red ones, if half of those chips really are red, is so small because I know here that half my chips are red, and look at how many few times out of 500 that happened. The probability is so small that we would say it's really unlikely that half of those chips are red. Your teacher is probably pulling your leg. The next thing that we need to talk about for sampling distributions are unbiased estimators. An estimator is really what we're going to use to, like I said, estimate. It's the statistic that we want to use to estimate the parameter. And an unbiased estimator is what we need to make sure that we are getting a good estimate. Some are biased and some are unbiased, and the unbiased ones are what we're looking for. And we're going to do something in class, or by now probably when you're watching this video we already have done something in class, called the German tank problem. And hopefully you will see, we will be able to look at some things that are unbiased versus biased. A statistic is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Okay. However, this is assuming that your sampling process was okay. If your sampling process is biased, like if you don't use a random sampling process, then this goes out the window entirely. But ones that are unbiased are like X bar. X bar is an unbiased estimator of the mean. And p hat is an unbiased estimator of p, which means that if I had the true sampling distribution, the mean of that sampling distribution. So in this case, if this were a true sampling distribution, the mean of all of these p hats would be 0.5 because that is my proportion in my population. However, what we will have is almost never a true sampling distribution. So therefore, you have to remember that it is not perfect, and that is okay. All it means that it is close and consistent. That's what we're looking for in our cases, because we'll never have the true sampling distribution. Close and consistent. Okay, so how can we reduce the variability of a statistic? So how can we make this be less varied, have a lesser range? And what you'll see is if you take larger samples. So let's go back and let's see if we can do some larger samples here. Let's change this and let's sample some more cases here. But instead of, let's turn the animation off. We don't want replacement because we want it to be a true sample. And instead of 20 like we did last time, let's double that and do 40. Okay, so you can see my sample now is of 40 instead of 20. Let's go in here and make a measure. Let's call it the proportion of red. And it is equal to the proportion whose color is equal to red. Okay, oh, notice this one right on the bat is 0.5. So now let's go in here and let's create a beginnings of a sampling distribution. And it's created 5 measures. Let's turn the animation off. And we wanted to take 5, we took 500 earlier, so let's take 500 now. Okay, so it has collected all the measures. Let's get a look at them. It's easier to do that from a graph form. Okay, you notice here now that even by increasing our sample size by just 20 you can tell by this, has lessened our range here. So it's made us have less of less variability in our statistics. So because now we go from 0.27 to 0.7. Where earlier we were going from like 0.18 to 0.8. So you can see that not is decreased the variability in our sample. And you can also look and see that, see this big tall one that sticks out much more, and that is definitely going to be the mean of our almost symmetrical distribution here, 0.5, right on the money. So this proportion here is an unbiased estimator. So how can you reduce the variability of a statistic? You can take a larger sample. Okay, and the question here is, what effect does the size of the population have on the variability of the statistic? And this goes back into our 10% rule. So as long as your sample size times 10 is less than or equal to your population size, the sample size or the population size really has no effect on the variability of your statistic. Only the sample size does.